surface integral. In this section, we will learn how to perform integration over a surface in three-dimensional space, such as a sphere or a paraboloid. We will use a parametrization of a surface to define a surface integral. We will use two variables, u and v, to parameterize a surface S in 3 space. The set of points x, y, z given by r vectors uv is equal to x uv I plus y uv j and z uv k are the parametric equations for the surface S. Each choice of u and v gives a point on S. By making all choices, we get of all S. We draw this x, y, z. This is r vector uv. This is S surface. Now, theorem. This theorem about the evaluating a surface integral. Let S be a surface with equations z is equal to g x y, and let d be its projection onto the xy plane. If g del g del x and del g del y are continuous, on D, and f x y z is continuous on S, then the surface integral of f over S is surface integral on S f x y z ds is equal to double integral on D f x y g x y roots 1 plus gx square plus gy square dA, where ds is the differential area element on the surface S, and dA is the projection of ds onto the xy plane. Now, surface integrals of vector functions. Before we consider such surface integrals, we need to define the orientation of a surface. An oriented surface is a smooth surface together with a particular choice of orienting unit normal vector defined on the surface S. For example, if we define n vector on the smooth surface, Z is g x y by normal vector is plus minus gxi minus gy j plus k divided roots 1 plus gx square plus gy square. The sign plus implies upward unit normal vector. The sign minus implies downward unit normal vector. Definition. If f is a continuous vector function, define on an oriented surface S with outer unit normal vector n. Sorry. Then the surface integral of f over s is surface integral over s f ds is equal to surface integral over s f n ds. This integral is also called the flux of f across s. Flux of f across S. Let's now theorem. Let S be an oriented surface. Given by Z is equal to Gxy, and let D be its projection onto the xy plane. The flux of F across S is surface integral on S F and ds is equal to plus minus double integral on D F minus Gxi minus Gyj plus K dA. For the sine plus the surface is oriented upward, and for the sine minus the surface is oriented downward. Now, new theorem. New theorem is divergence theorem. This theorem is divergence theorem. Or Gauss theorem. Let F be a vector function that is continuously differentiable on a space region B bounded by a closed, smooth, or piecewise smooth surface S. Then triple integral on B divergence f vectorial function dv is equal to surface integral closed smooth surface on S f and ds, and is equal to f ds, where n is an outwardly drawn normal. The divergence theorem establishes equality between triple integral of a function over a region of three-dimensional space and the surface integral of the function over the surface that bounds that region. New theorem. This theorem is Stokes theorem. Let S be an oriented surface with outer unit normal vector n bounded by a smooth or piecewise smooth simple closed curve C with a positive orientation. With a positive orientation. If f, x, y, z is a vector function whose components component functions have continuous first partial derivatives. On a region containing S and C. Then line integral on C, close C, f dr is equal to surface integral on C and curl f ds is equal to surface integral on S curl f ds.